EES, which is pronounced ease, is an acronym for Engineering Equation Solver. In this section we have discussed ideal gases that are built into EASE, as well as those that are in the NASA database, which is also part of EASE. Both of these ideal gases use reference states that are designed in order to make problems involving chemical reactions easier. The reference states for specific enthalpy and specific entropy are important for applications in which chemical reactions occur. This is discussed in any thermodynamics book, including Klein and Nellis 2012. The reference state used to provide the specific enthalpy for all of the ideal gases implemented in EASE is based on the stable elements having a zero specific enthalpy at 25 degrees Celsius. Therefore, the absolute value of the specific enthalpy returned by the ideal gas database includes the enthalpy of formation, which is associated with forming chemical bonds. The reference state used to provide specific entropy for all ideal gases in EASE is based on the third law of thermodynamics, which dictates that the entropy of any pure substance must be zero at 0 Kelvin. And these choices again make it very easy to work with chemical reactions. So as an example, the stoichiometric reaction between methane and oxygen is given here. The lower heating value of methane on a molar basis is defined to be the difference between the enthalpy of the reactants and the enthalpy of the products for this reaction if they're both evaluated at 25 degrees per mole of methane. And the lower heating value assumes that the water in the products is all in the gas phase. This calculation can be easily accomplished using EASE because the reference states that are used for the ideal gases include the specific enthalpy associated with the chemical bonds in the molecules, and therefore the specific enthalpy reported by EASE for an ideal gas is the standardized specific enthalpy that should be directly used in energy balances for chemical reactions. So in this type of application, it's usually best to set the unit system to be on a molar basis so that all specific properties are reported per mole of gas rather than per mass. So here we'll use the dollar unit system directive to specify that we're going to work on a molar basis. Then we'll get the molar specific enthalpies of each of the substances involved in the reaction using the enthalpy function. And you'll notice here that we're going to assume that the substances behave as an ideal gas. So this corresponds to using the chemical formula rather than the fluid name as the fluid. So for example, O2 rather than oxygen, or CO2 rather than carbon dioxide. The total enthalpy of the reactants and the total enthalpy of the products of the reaction per mole of CH4 are computed here, and we can subtract them to determine the lower heating value. And solving then leads to 8.03 times 10 to the 8th joules per kilogram mole. If you want to divide by the molar mass of CH4, then you can have the lower heating value on a unit mass basis. Note that there is a lower heating value function that you could have used for these kind of calculations. So if I just call lower heating value, I'll get the same answer we just computed. So this is one of a series of tutorials meant to describe the operation of the EASE software. If you'd like to get more information about EASE, obtain the software, or access more of these tutorials, please go to the website fchart.com. These tutorials are excerpted from the book Mastering EASE, which can also be obtained from the FChart website.